the Orange County Fair, held in Southern California. In theory, these crowds hold a predictive power that can have startling accuracy. But it doesn't belong to any individual, only the group. And even then, it has to be viewed through the lens of mathematics. The theory is known as the wisdom of crowds, a phenomenon first documented about 100 years ago. Statistician Talithia Williams is here to see if the theory checks out, and to spend some time with the fair's most beloved animal, Patches, a 14-year-old ox.
It was a fair kind of like this one, where in 1906, Sir Francis Galton came across a contest where you had to guess the weight of an ox, like Patches you see here behind me.
After the ox weight-guessing contest was over, Galton took all the entries home and analyzed them statistically. To his surprise, while none of the individual guesses were correct, the average of all the guesses was off by less than 1%. That's the wisdom of crowds. But is it still true?
So here's how I think we can test that today. What if we ask a random sample of people here at the fair if they can guess how many jelly beans they think are in the jar? And then we take those numbers and average them and see if that's actually close to the true number of jelly beans. Guess how many jelly beans are in here? Come on, guys. Everybody's got to have their guess. I see your mind churning.
1227. 846. Probably like 925.
Think it though. So just write your number down. There you go.
The 135 guesses gathered from the crowd vary wildly.
The range of our guesses was from the smallest was 183, the largest was 12,000. So you can tell folks were really guessing. But when we take the average of our guesses, we get 1,522. So the question is, how close is our average to the actual number of jelly beans? Well, now's the moment of truth. All right, so the real number of jelly beans was 1,676. The average of our guesses was off by less than 10%. So there actually was some wisdom in our crowd.
Though off by about 10%, the average of the crowd's estimates was still more accurate than the vast majority of the individual guesses. Even so, the wisdom of crowds does have limits. It can be easily undermined by outside influences and tends to work best on questions with clear answers, like a number. The steps Talithia took reflect a process going on all around us these days in the work of statisticians.
Thanks, everybody. So we collected this data, right? We analyzed it mathematically, and we got an estimate that was pretty close to the actual true value. That's math and statistics at work.
We didn't always use math and statistics to make predictions. The Romans studied the flights and cries of birds. The Chinese cracked oracle phones with a hot metal rod and read the results. 19th century Russians used chickens. Throughout history, we've sought the future. In moles on people's faces, clouds in the sky, or a pearl cast into an iron pot. And that list of things used for predicting goes on and on. But more recently, that is the last couple hundred years, to see into the future, we've turned to science and made some remarkable predictions. From the existence of Neptune, or radio waves, or black holes, to the future location of a comet with such precision we could land a space probe on it. But if you pop the hood of science, Inside, you'll find a field of applied mathematics that's made many of those predictions possible. Statistics.
Statistics is kind of unique. It's not an empirical science itself, but it's not pure math.
Alrighty then. So the jelly bean thing was actually the thing I wanted us to see. The power of what was that? The crowd, the knowledge of crowds, the wisdom of crowds, whatever they had, the specific name they had for that. But again, that's our example of sampling. We're going to take a random sample of individuals in a population, and we're going to then take the mean of that sample, and then we're going to infer if I've done everything correctly and gone and checked all my boxes off, we can infer then that's going to be the mean of my population. And that was the jelly beans was a really good example of that. So that's why I wanted to show that. Anyway, we're going to jump over here, and if I can get everything ready to go, we'll get some notes taken. I can't even think of, let's see here. We're not doing notes, key. There we go. So here's where we're at. All right. So we're moving into the sampling distributions for a one sample proportion. So now what we're going to do is we're going to talk about proportions. And to better do that, I forgot I actually have this pulled up. Oh, you don't need to see my fantasy football league. It's okay. I have most points for last week. Anyway, here we go. So what we're going to do is we have a Reese's Pieces machine. And inside this machine, we know that 40% of the Reese's Pieces in this machine is going to be orange. And we're going to pull these out 10 at a time. So then we can animate this. So this works exactly the same way, except I want to do it as a proportion. So in my first example, we drew out 10 M&Ms, 80%, which 80% of them were orange, where 40% of my population was orange. So that one's actually a really amazing one to get. So right off the bat. So again, just to, we'll draw that sample. So again, there's another sample of 10. The p hat, which we'll get to later, 4 of them were orange, so that down below we plotted that point, and we could continue to do this over and over again if I wanted to. As far as the next one, we got 6. Okay, so again, I will continue to draw those samples. We don't need to animate this anymore. I'm just going to hit draw samples, and away we go. So we are, again, over time. This is just a bunch of samples of size 10. And we can see what my distribution looks like as we do this. So remember the p hat is going to be the proportion of successes, in this case an orange M&M. And after I hit that a bunch of times, we can see again that we have something that looks approximately normal. We can click this on. That's what a normal curve looks like. So we can see that it's approximately normal. Okay, but the point is, even when we get to a proportion, like if the proportion of people that vote would likely vote for, then we can also use our same statistical measures with that as well. Was the goal. So here, if I jump up my candy size to 20. Let's see what happens there. So number of samples, we're going to do 100 samples, not PP samples, 100 samples. So draw samples, and there's my 100 samples. And we can see again, it's very odd that we have, that, I don't say it's an anomaly, but again, we should have something that is normal looking, okay? Again, that's what the M&M thing, except the only difference is now we're talking about proportion. So if you look at the center of my proportion, it was at 0.4, which was roughly the center of my curve. So let's change this to a different proportion and see what happens. Let's say that 80% of my machine was yellow. So again, we're going to draw samples. There's my 100 samples. But if we look, the center of my curve has now shifted over to be the center roughly of my population. So 0.8 was the proportion of orange Reese's Pieces in there. And if we look at my distribution now, my distribution of p hats, we can see then that that set was centered at 0.8. Okay, so that was the whole purpose of looking at the candy machine here, just to understand that just like a sample mean, the sample mean we can then assume is the same as the population mean. The same thing happens with a proportion, and because we have a proportion, that sampling distribution of proportion is also going to be able to allow us to do normal calculations. So now we can come out here and fill out our notes for a sampling proportion. So again, if we look, we'll jump out of here real fast again, just over into our formula sheets. We can see that my formula sheets also has, why was I clear down there? Anyway, here it is. We were down here with we were down here for means previously. Okay. So now we're going to be up here. We're going to be doing proportions. Okay, so again, we can see that if we look at the notation, the mean of my sampling proportions is going to equal the population proportion. So again, this is also understanding notation. A hat always means a sample. Without the hat means a population. Okay, and now we also have a formula for calculating the standard deviation of p hat. Okay, p times 1 minus p divided by n. That's coming from knowing the population proportion. We can also do it from a sampling proportion as well. So we have all sorts of, again, you don't have to memorize any of the formulas. You just have to know where to find them, which is going to be there. All right. Back to this. So when we roll through this, we denote a sample proportion by the notation p hat, and I guess we can't have the arrow there. So p hat is going to be our sample proportion. If we're not given p hat, it is the number of successes divided by the number of, by my sample size. I was gonna say number of trials, but really it's my sample size. So from the other sheet, we saw that the mean of my distribution of samples is going to be equal to the proportion of my population. We were also over on that other sheet, we were given the standard deviation of p hat. That was a formula that we had to remember. This is p times 1 minus p and divided by n. So just to make sure that we understand that that's all under n, I'll extend that. Okay. Now, when we do these calculations, we always had to make the assumption that we had some normality involved. Previously, when we talked about means, normality could be my original population was normal to start with, my sample size was greater than 30, or that my, or if we had actual data, my box plots were roughly symmetric. Now when we're talking about a proportion, our proportion has a new rule for this. So when my sample size is large, the sampling distribution of p hat is approximately normal. To assume the sampling distribution is approximately normal, we follow that it's the following rule: n times p is greater than or equal to 10. N times 1 minus p is also greater than or equal to 10. Now, since this is a situation where it either is or is not, that means in reality, where we can look at it, we have to have greater than 10 successes or greater than 10 failures. Okay, or we need to have both of that. So that means that if we're doing a proportion, there's no way I can take a sample size of 10 because I have to and be able to do any type of inference on it, okay? Just because I have to have at least 10 successes and failures. So the minimum sample size of anything we do with proportions has to be 20, and that's if we can split it down the middle at 50-50. Okay, so that again, if we're like later on, I don't know. I'm trying to figure out how we're going to do it. We do a couple activities. I'm not sure how I'm going to be able to do them with you guys. I'll definitely have to prep that a little bit. But anyway, that's what we're looking at, successes and failures. So this is actually very binomial in nature. If we're given calculations, we're asked to perform a calculation and we have no idea what P is, then we're going to assume 0.5 because that's going to cause it to be as large as possible. And we'll get to that, more of that later. Just remember that we could pop in a 0.5 if we're not given a P value. Okay, so here's where we're at. I mean, again, it's understanding the normality of things, and we'll apply this to a problem. So if the true proportion of defectives by a certain manufacturing process is 0.08, and a random sample of 400 is chosen, can we describe the situation as normal? Well, again, it's normal if I can have at least 10 successes and 10 failures in my group, okay? And we're going to check that, and how we check that is we're going to take 0.08 times 400, and I need to make sure that that is greater than 10. So that checks out, okay? We're going to take its complement. We're going to have 92 that we're okay. We're going to take that times a sample size of 400, and I end up with 368 failures. Or no, 368 were good, not that they're failures. So both groups were greater than 10. So here's what happens. I see it all the time. Maybe you guys will be the different group. That is, I'm going to ask you, is the normal calculations appropriate here? And you're going to say yes, because 400 is greater than 30. And I will wield my red pen and say, well, actually I wouldn't on yours, red marker. I'm saying, no, that's not right, because we're talking about proportions. So we have to make sure when we read through a problem, that's the first thing we're going to look for. Am I dealing with a mean or am I dealing with a proportion? Because we're going to have different tests for each one. Okay, so P, remember this is a population parameter. We know that that population has an 8% defect rate. Okay. What is the probability the proportion of defectives in the sample is greater than? So with that, so that's the mean of my population. We'll then also assume that's going to be the mean of my sample. And that means that we also need a standard deviation. That standard deviation, again, is very much formula based. 0.08 times 0.92 divided by 400. And that is going to equal 0.0136. Okay, so now we're ready to roll through this. We want the likelihood. What is the likelihood that we have an X value? So did it tell me? No, it didn't tell me. X is the proportion of defective whatever. Okay, so we want what is likelihood that we're going to have a defective rate greater than 10%? We're expecting 8%. What is the likelihood that is 10% or higher? So again, all of this eventually works, I don't say exactly the same. I'm going to observe 10%. I'm going to expect 8%. And we figured out my standard deviation was 0.0136. So that means that we're going to get a 1.47. And again, I'm able to look that up as a 0.9293. But because it's a right-hand tail, we're going to have to go with 1 minus 0.9293. And so we're going to end up with 0.0707. And again, just to have it in your notes, or maybe you've already been there, if we're doing, we could use a normal CDF here. The normal CDF, again, my left boundary is 0.1. My lower boundary, my upper boundary is 1E99. My mean, we said, was 0.08. And I'm not sure I have enough room to squeak it in, but we'll try. The standard deviation of p hat. Whoops. Nice. 0.0136 was the standard deviation of p hat. We kind of snuck it in there. Okay. Example 8. Suppose 3% of the people contacted by phone are receptive to a certain sales pitch and you buy your product. If your staff contacts 2,000 people, can we describe this as approximately normal? Okay. Again, since it's a proportion, we have to know how we can tell the difference between a normal proportion versus a normal mean. Okay. Again, our normal proportion is going to be, and I'll just write out the answer. It is going to be yes. And again, typically we're not going to try to trip you up unless the question is only asking you about whether we can assume normality or not. That's when it might try to be deceptive. But if we're actually going through the process, likelihood it's going to be okay. Anyway, we're going to take 0.03. We have 2,000 people in my sample, so that means I'm going to expect 60 people to be receptive. 97 times 2,000. I'm going to expect 1,940 to be non-receptive. That would be hard to keep your motivation. But anyway, both groups are greater than 10. So we're going to go over here and say that X is going to be the proportion of people that were receptive, and then we'll try to go through this calculation. What's the probability that more than 100 people contacted will purchase your product? Okay, so actually, in reality, they gave me a hard number, and I can go ahead and work with the hard number if I want, or I can change it to a percentage. I went ahead and changed it to a percentage just because I could. Okay, so again, we're going to assume we know that 3% of people are receptive to it. So that means I'm going to expect my sampling distribution to have a mean of roughly 3%. That standard deviation is going to be found by taking my success rate times my failure rate and divided by sample size. So we know that we're going to have a 0.0038. Again, if I want 100 out of 2,000, how big is my sample size? Yes, 2,000. Those are going to cancel, so I need to know what 1/20th is, which is going to be 0.05. So the reason I said that, we want to come over here. We want what is the likelihood that X is greater than 0.05? So again, we have our curve. We're expecting 0.3 in the middle. I want the likelihood of 0.5, and we want to be greater than 0.5. So again, this problem works exactly the same way the last one did. Okay, so we're going to have that z-score. 0.05 is the observed value, 0.03 is going to be the expected value, and my standard deviation is this microscopic 0.0038, which gives me a z-score of 5.26. So remember what we have here is we have my mark of 10, my mark of 5% is out here at 5.26 standard deviations above the mean. So my chart doesn't even actually tell me what this is. Okay, because if I look at this, this is going to give me approximately 1. Okay, because that is going to be, remember, then when you look that up in the table, your table is not going to have a 526, but it's finding the area to the left. So that's approximately 1 because it is clear out here at 5.26. So that means if we're talking about my right-hand tail is actually going to be then approximately 0. Okay, because we had to subtract from 1. 1 minus 1 is 0. So maybe I should get that in there. Okay. So this has no chance. Okay. We'll continue matriculating our way through the notes here. So now we talked about one sample. So now we're going to rotate this over to two samples. So the sampling distribution of a two sample proportion, we have the following. So again, now because we have two populations that we're dealing from, the only difference is we're going to denote that they're going to have some subscripts to denote the difference between the two. Okay, so what's going to happen then is we're expecting the mean of P1 minus P2. So the mean of the difference in my populations will be the same as the difference in my proportions. So I don't know why. Is that how it looks on the sheet? I feel like I'm botching this for some reason. Let's go look. Yes. All right. So there we go. That's what I should be writing down. So this is actually 4 p hat 1 minus p hat 2. But yeah. Let's go back to nope. No. So again, we're going back to the middle of my sampling distribution is going to be the middle of the difference between the two populations. Okay, if the two proportions are equal, I'd expect that to be 0, but we move on. Now this becomes ugly. So we have sampling distribution 1, its variability, sampling distribution number 2, and we're going to put that variability together. And again, my approximately normal is going to be the same as above, except it has to be true for both populations. Researchers of the National Cancer Institute released the results of a study that investigated the effect of a weed-killing herbicide on house pets. They examined 827 dogs from homes where the herbicide was used on a regular basis, diagnosing malignant lymphoma in 473 of them. Of 130 dogs from homes where no herbicides were used, only 19 were found to have lymphoma. Tongue, lips, teeth work together. All right. So can we describe the situation as normal? Okay. Again, this is just going to be a personal preference thing, and it's just a habit thing that we probably should start developing. We should just start writing things down as we see it. So we're going to have a sample that had herbicide in the home. That sample, there were 473 were found with lymphoma out of 827 homes that used the herbicide. So that means that 57% of the dogs that were in herbicide homes had that lymphoma. Okay. The next piece of data that it gave me was the probability of no herbicide. That's what that NH is. Let's see here. We can do this different. So that means that 19 out of 130 homes, and that turns out to be 15. So the number of herbicides, and again, this is just going through and writing down everything. If I go through and I label everything as I read it, then I don't have to worry about labeling it through the process. Okay. Can we describe this as approximately normal? Well, in this case, I have to do a check. And again, the greatest common foul here is you're going to say, well, yeah, both samples were over 30. I'm good to go. Well, that's true if we had the mean. Okay. But we don't have the mean. We have a proportion. So that means we have to say, we're going to say yes, because we're going to have two groups in the herbicide group. go. Again, this is a little bit how you want to look at it. I could say that I had let's see, what was it? 473 with lymphoma. And then we had 300 and so what would be the complement of that? I need a calculator. Why don't I have this written down? 354? Does that make sense? Yeah. Okay, so as long as we can say both groups are greater than 10, then we're good. So in reality, we did not have to, I could have used the proportion that I calculated up here, okay, is the 0.57 and then that, but there's really no sense in undoing the math that I did. I know that I have 473 successes from the get-go, and that means its complement of non-lymphoma is 10. So since both groups are greater than 10, I'm good to go, okay? If we go over here and look at my non-herbicide group, again, we have 19 were found to have had lymphoma. And that means that 111 without lymphoma, both are greater than 10, okay? So that means that all groups greater than 10. And unfortunately, that's what you have to show me. You have to show me that both groups were greater than 10. We had success to over 10 successes and failures in both. Okay. What is the standard error of the difference of the two proportions? So we're going to know, well, actually, we need a variable for that then. So we're going to let D equal the difference in proportions. So we need the standard deviation of D. So again, it's very formula driven. 57% had lymphoma. That means that 43 did not. And we had 827 dogs in my first group. Excuse me. In my other group, it was 15. And that means that has to be an 85. And there was 130. So we get 0.036. So again, that becomes, sometimes we get calculator in there because we have to drop that into our calculator and try to figure out where that comes. Later on, it gets a little bit easier, but we'll cross that bridge when we get there. Okay, what is the likelihood difference between, I guess that's supposed to be, what is the likelihood there is a difference between the two groups? Okay, meaning I have a center. Well, I would need a center. Do we know what the center is? We haven't found out what the center. We know what the standard deviation is. We're going to expect the mean of herbicide minus non-herbicide to be 0. However, we observed it to be something else. We observed it to be 42. Okay. No, that's what we're expecting it to be. Wow, I'm good. I am botching this up. So we want the probability that D is less than 0. Okay. We want to know, or excuse me, not less than 0. We want to know if there's a difference. So, well, it could be less than 0. It just depends on what you want to do. Okay. We want to know, is there a difference between groups? So we're expecting the difference between groups to be lining up with my sample, and that was at 42%. What we're worried about here is back here at 0. Okay. What is the likelihood that it is greater than 0? So that means if we go to our z-score, we observed 0. See, I feel like I botched this. But I'm going off my notes. we're trying to figure out what is the likelihood that it is 0, but I observed, but we're expecting it to go off my samples to agree with my mean. That's the negative 11.67. So again, this is approximately 0. And since it's a right-hand tail, 1 minus 0 is going to equal 1. So we're going to assume then there's a 100% chance that there's a difference between two groups. No. The question is, what is the likelihood that the difference between the two groups, I guess I need to rewrite this. What is the likelihood the difference between the two groups is 0? It needs to be 0. So that's why I think I have it backwards in my notes, and I'm sorry that I botched this down and worked through it back. I knew the entire time I was writing it down, this didn't feel right. Okay, let's try again. And because here's what happens. So we observed a difference of 42. We're expecting a difference of 0. So that means that we're going to get a positive 11.67. So I guess my picture is wrong because this should be a 0 here, and now, oh my gosh, completely blew this one up. Okay. My probability statement has to change. No. Can I blame it on Monday? I don't know. Here we go. I don't know. Okay. All right. So I'm assuming that my population is the same as my samples. So that's going to be 0.42. I'm observing what's the likelihood that I'm going to see a 0 in there. So that does bring it back to a negative 11.67. But if I want to, yes. What's the likelihood there is a difference between the two groups? There's a 100% chance there's a difference between the two groups. So I guess I had it all over. I had it okay from the very get-go. I just wasn't trusting myself, and I don't know where I was. It's just one of those things. Sometimes we're gonna get confused. I get that. Even I get confused. So that's where we should have ended up with. Except now my graph is wrong again. But we'll hope the next one's better. Yes, there's a 100% chance there's a difference between groups. Okay. All right, we'll try this example 10 because I think that's our last example. It is our last example. We'll see how bad this one crucifies me. And we'll go from there. Ugh, I hate it when I do that. Painful wrist condition known as carpal tunnel syndrome can be treated with surgery or a less invasive wrist splints. In the September 2002 Time magazine article reported a study on 176 patients. Among the half that had surgery, 80% showed improvement after 3 months. All right, so we're going to have two groups. we're going to have a surgery group, and we're going to have a splint group. So as we write things down as we see it, so we had the proportion of the surgery group. Of that, 80% felt like they showed improvement after 3 months. But then we have the splint group. And that was 54%. I guess we could have had in the splint group, we had, let's see here. We split that in half. We did. So we had 176 patients. So that means we had 88 in the surgery group. And then we had 88 in the splint group. Can we describe the situation as normal? So this is a case of we actually have to do N times P. We have to have 80% felt had improvement after 3 months. There were 88 in the group, so that means that 70 of them showed improvement. 20% did not. So that means that was 18. So this was in the surgery group. In the splint group, 54% of them showed improvement after 3 months. There was 88 people in there, so that means that 47 showed improvement. And 41 did not. So it is yes, because subgroups are greater than 10. All right, again, we're looking for that, the difference. Did I establish, excuse me, I wrote down D, but did I establish what D is? I did not. D is the difference between surgery and splint. Point 8 had saw improvement. 0.2 did not, so we divide by 88. My splint group, that was my surgery group. Now we have the splint group. So we end up with a standard deviation of 0.068. It did not ask me for it, but to find the mean difference that we're going to use. Okay, that's going to be 0.8 minus 0.54, or 0.26. Okay, so we're on a curve. We have a 0.26 in the middle. Here is 0. So we're after what is the, so in reality, what the question should be in reality, what is the likelihood that, how often would we expect then the surgery group to show better results than the splint group? Okay. In this case, it just says, what's the likelihood that the difference is 0, okay, or greater. Okay, so I guess I need to rewrite the question, because really I need to write it as, what's the likelihood that we would observe a difference? Okay. Knowing that the reality is my proportions are going to be off by 0.26, what is the likelihood that I'll see a difference? And again, we're going to get to that 100% thing. Okay, that's why I have some X's next to these problems, and now I understand why I have X's next to these problems. They stink. but I forgot to go. I didn't go through them well enough ahead of time to remember that. I'm sorry I've failed you. So we're going to expect 0 to be sitting that there at negative 3.82 standard deviations, where again, that is going to be something that's approximately 0, but we got to go 1 minus 0. So that means this is approximately 100%. Okay, so if we had this as data, we could say with 100%, the likelihood that we see a difference is going to be 1. Okay. All right, crash, burn, flames, bail now. All right, so we're going to stop my share. I'm going to stop recording.